Alright, so let's do this. What are we doing? We are doing tangent slopes using polar equations. And so we've got a little silly examples here. A famous graph in polar coordinates, we pick some random angle, 20 degrees. That means we're looking at around the 20 degree mark. So let's make a little note of it. 20 degrees is right around this way. That would be 20 degrees. And we're looking for the tangent slope. So we need to find a tangent line. Let's pick a different color like blue. And we'll draw a tangent line there. That tangent line would look something like that. And so here we have 20 degrees, and here we have the tangent line at 20 degrees. And what we want is the tangent slope. So what we're really after is we want dy dx. That is the tangent slope at 20 degrees. What are we going to do to solve it? Well, we do something similar than what we did when we did parametric equations. We use this idea that we could divide the top and the bottom by the d theta differential. And why in the world would we want to do that? Well, because a long time ago we had this. Whoa. We had this. What was it? Where were we? Oh, when we had this triangle, we had said that the dictionary to translate from x's to r theta was given by analyzing this triangle using adjacent over hypotenuse and whatnot. That gave us something like this, I remember, right there. Well, I just passed it. That's what it gave us before. R is equal to cosine theta, sine theta, and tangent of theta is equal to that. Those are crucial. These are the defining features for the defining relationship between x's and y's and r's and thetas. So I'm going to make use of that right about now when we're doing the one we're doing right now. Okay, we just need to go ahead to that page. See, right now they're out of sync. Right there. So the defining feature was, I'll write it up here again, that was y is equal to, I'll do it right here since I've got space here, y was equal to r sine theta and x was equal to r cosine theta. That was absolutely crucial. From here I'm going to get my dy relationship and dy d theta, and from here I'll get dx d theta. So we will do that by differentiating both sides. So dy d theta is equal to the derivative of the first, which would be dr d theta times sine theta plus r times the derivative of sine, which would be cosine theta. Okay, that's it. That's what goes on the numerator over here. Dy d theta would be sine theta and a dr d theta. That's this piece plus r cosine theta. Now we go with the x. On the x we have that dx d theta. Again, we do product rule. That's the derivative of the r times the cosine, dr d theta, plus the r times the derivative of the cosine. That would mean that it's going to be a minus r times the derivative of cosine would be sine theta, negative sine theta. That's what goes here in the denominator. By using product rule on this, we got that. That's what goes here. So we have that this is cosine theta. Oh, I forgot my theta there. Dr d theta plus, actually minus, r sine theta. Right? Now what? And now we have our relationship here for r is equal to that. So from here, I could figure out that bit right there, dr d theta. That one can be computed by calculating dr d theta from here. The sine theta, well, I'll just plug in 20 degrees when I'm done. The cosine theta also, the dr d theta here will have to be obtained from here. So let's just do it right now. Talk is cheap. R is equal to 3 plus sine theta from here. In fact, yeah, why don't we do that in red, yeah, so it's more obvious where we got the r from. So we'll go with little red here. R is equal to 3 plus 5 sine theta. slap a d on both sides, it's d theta, so therefore dr d theta is equal to the derivative of 3 is 0. 5 you can pull out, so it's 5 times cosine theta. That's dr d theta. So when all that is said and done, then dy, let's go back to yellow. So then when all that is said and done, then dy dx is equal to sine theta, dr d theta, I got that here, times 5 cosine theta, plus r, well the r was over here, that's r, sorry, that's 3 plus 5 sine theta, times cosine, that would be times cosine theta, all that over cosine theta, times dr d theta. I've got dr d theta here, so it's times 5 cosine theta, minus r, that would be 3 plus 5 sine theta, I'm getting my r from here, and then sine theta here. And now we have an amazing expression that at any given angle theta, boom, you choose at any theta, 111 degrees, plug it in there and you get the slope of the tangent line. Amazing. A template here for all the tangent slopes looking at any angle. All you do is plug in the angle and you get the tangent slope. In particular, for our problem here, we want to plug in theta is equal to 20 degrees. And so everywhere you see theta here, you would plug in 20 degrees. But that looks like a lot of grunt work. I'm way too sexy for the grunt work. I'll let you guys do that. Alright, that's how you find tangent slopes, part 1. Come back and we'll do another example of finding tangent slopes, maybe. I went ahead and I plugged this into a calculator and I've got the answer. The answer looks roughly like this. If I plugged in the function, this was the function that I've got from the derivative work that we just got done doing. That's this function. At any given angle, it gives you the precise slope of the tangent line. So at 20 degrees, I plugged it in there. This is just to change the degrees, and you get the 2.15. What exactly does that mean? That's the rise over run for that line, the blue line, the rise over run. Every time you run one, you rise 2 point something, as indicated on the calculator. What's nice about this is that you could, this is a nice formula. At any given angle, I could tell you exactly what the tangent slope is. Pick 90 degrees. What do you suppose what do you think it would be at 90 degrees? Well, pretty close to 0. It should be flat. The tangent slope should be 0. The little calculator confirms exactly that. Anyways, that's a tangent slope.